So today the topic for the webinar will be the adoption of additive manufacturing into your current manufacturing processes and how you can integrate 3D printing into your current workflow. For the first topic, we'll be giving you a quick introduction to Maha Chemicals company and our additive manufacturing capabilities. And on the second topic, we will touch on the shift in paradigm of modern manufacturing, which will include some case study on cost analysis of injection molded part versus additive manufactured part. And on topic 3, we will discuss on the open and closed system in additive manufacturing. We'll explain the difference between the two systems. Moving on to topic 4, we will show you some benefits of additive manufacturing in businesses and how you can integrate AM technology into the current manufacturing process. And on topic 5, we will show you the additive manufacturing capabilities that Maha Chemicals is currently representing. On topic 1, I will give you a quick introduction to our company. So Maha Chemicals has been established for 45 years. We have about 175 employees in the whole Southeast Asia, and we have 11 regional offices in the region. We are currently working with over 1,000 suppliers, over 3,000 customers, and we have 12 warehousing sites regionally. Currently, we are working with over 3,000 different types of inventories. So here's a look at our business units. For the first 3 business units, Surface Technology, Engineering Materials, and Living Sciences, they deal with the distribution of specialty chemicals to industries like paint and coating industries, construction industries, plastic, rubber, lubricant industries, and also companies, pharmaceutical companies, and soap manufacturing companies. As for my business unit, Industrial Solutions, we distribute lab and analytical instruments, as well as provide consultation and process manufacturing solutions. Our 3D printing business actually lies under the process and manufacturing solutions. Okay, moving on to topic 2, I will pass the mic to Yuta, our application engineer, which he will go through the rest of the webinar. Yuta.
Hello. Thank you, Jason. Okay, I'm Yuta, the field application engineer for our Maha Chemicals 3D printing division. So first, we'll talk about the shift in modern manufacturing paradigm. So the journey. Throughout human history, we are always trying to become better, faster, and stronger. So this has actually led to several revolutions in trying to produce things faster as well. So during the first industrial revolution, Industry 1.0, this has led to mechanization using steam power and water power. Then second, okay, where mass production assembly line and electrical power has been used, created by Henry Ford. Third is where the third industrial revolution is where automation and digitalization happens. Processes are commonly automated using logic processors, operating largely without human interference, but there's still a human aspect behind it. The process is automated based on individual input, but not data. Okay, this is where Industry 4.0 happens, where we are trying to start in the third with the adoption of computers and automation, and enhance it using smart and autonomous system fueled by data and machine learning. So Industry 4.0, we have a big network of computers that are connected and communicate with each other to ultimately make decisions without human involvement. The systems are getting smarter as they get more access to data, making our factories become more efficient and productive and less wasteful. Ultimately, it's the network of these machines that are digitally connected with one another and create shared information that result in the true power of Industry 4.0. So today we'll be touching on a small part where 3D printing or additive manufacturing as the part of the Industry 4.0 network. So the definition of additive manufacturing. So it's the official industrial standard term under ASTM F2792. Okay. It's defined as the process of joining materials to make objects from a 3D model data, usually layer upon layer, as opposed to subtractive manufacturing methodologies. Synonyms of AM includes all this. Okay, so I'm sure most of us will be familiar with the term 3D printing, which is the last term on the synonyms. So under additive manufacturing, ASTM has separated them into 3 different types of starting materials and 7 different types of processes. We will not be touching on all these processes today, as it will become a very long lecture. So for the market value on the 3D printing business, so 3D printing is projected to be a multi-billion-dollar market and growing. So researchers estimate that the 3D printing market will reach 7.3 billion in 2016. So the primary market includes 3D printing systems, materials, supplies, and services. This has grown at least 30% each year from 2012 to 2014. The rest of the growth comes from the secondary market, including tooling, molding, and casting. So within this market revenue by geometry, Western countries, North America, Europe account for more than 2/3 of the 3D printing market revenue, and Asia Pacific accounts for 27%. This puts Asia at a very big room for improvement to grow on 3D printing. So despite the significant growth, there's a wealth of untapped potential in 3D printing. In fact, 3D printing represents only 0.04% of the global manufacturing market, with prototyping as the leading use today. Wallace and Associates believe that 3D printing will eventually capture 5% of the global manufacturing capacity, which will make 3D printing a $640 billion industry. Much of the opportunities lies in parts production, the fastest growing 3D printing application. The use of 3D printing for parts production grew from virtually 0 in 2003 to 43%, which is 1.8 billion of global 3D printing products and services. 3D printing parts are currently being used for functional parts, 29%, prototype 18%, and visual aid 10%. This is a market ripe for disruption. Technology adopters that move beyond 3D printing to prototyping to use 3D printing in supporting and streamlining production can achieve new manufacturing efficiencies. Plus, there's an enormous opportunity for companies that get it right. So 3D printing is not a one-size-fits-all solutions for high volume standardized application. Traditional manufacturing is most likely the answer. When is 3D printing the answer? The top reason for pursuing 3D printings are prototyping, project development, and innovation. 3D printing can speed development and delivery of customized product and bring increased flexibility through better inventory management and real-time production of product with variable demand. There are other advantages, including manufacturing advantage for small batches, cost advantages based on efficiencies for certain application. However, low process stability can negatively impact quality, and low reproducibility can negatively impact product durability. It is critical to consider needs and priorities to make decisions between 3D printing and traditional manufacturing. Like everything else, there are benefits and trade-offs. So this is a comparison between 3D printing and manufacturing. So for 3D printing, small batches and highly customized parts are possible, while for traditional, it's for large part and non-customized parts. The cost per unit is very low for traditional manufacturing with high fixed costs, while 3D printing affords high variable cost but no fixed cost. The time to market when using 3D printing can be very fast, with reiterations of designs within a day, while traditional manufacturing will require the redesigns of molds, which will definitely increase lead time. With cost of complexity, traditional manufacturing would be much higher for simpler parts with the increase in complexity of molds. But for 3D printing, complex parts would cost no higher than simple parts. Next, we'll move on to a case study by a researcher online. So the case study one will be on drone legs. So this is a picture of a drone leg, which is considered quite complex. As you can see from the graph, the cost of 3D printing parts generally level out at about the same price as each other, regardless of the technology used. But as quantity increases at about 250 parts, it makes sense to start considering injection molding for a project of this geometry. With scaling that quickly goes to $1 a unit and $3 at quantities over 8,000, including the cost of tooling. Given the curve, it is clear that the price would further decrease as quantity increases. Next, we'll compare a potentiometer knob, okay, which tells a different story than a drone leg. Because of its small size, it remains cost competitive, using 3D printing for quantities over 2,000 units before the break even to injection molding. However, if over 2,000 units are needed, then injection molding can save you thousands of dollars through the product's lifetime. In fact, the per unit price without tooling would further decrease to less than 80 cents. Saving could be even higher if a multi-cavity mold tool is chosen. Next, we'll move on to case study number 3, junction housing. So this junction housing is an interesting case because it is typically considered as a large part for 3D printing platforms. This gives a higher per unit price from the get-go and also very little discount over quantities for these processes. Like the other part in this study, injection molding is ultimately the killer choice for production manufacturing. The upfront tooling to mold this piece is over $10,000, but the unit price is so low that at 250 units, it becomes drastically more economical by an order of magnitude to move to injection molding tooling. So this will let us focus more on small series production for 3D printing. So comparing between 3D printing and injection molding, firstly, the lead time. Lead time for AM is very low, within a day. But for injection molding, the lead time of the mold would depend on the size and the complexity of the mold, which for small batch production can be about 450 units to 1,000. Typical lead time could be 2 to 3 weeks for a single cavity prototype mold, while for multi-cavity injection or more complex molds, which could take as long as between 1 month to half a year, for production volume between 100,000 units to 1 million injection molded parts. Multiple cooling channels, multiple actions like sliding cans and lifters, as well as complex injection mechanism will add to the lead time. So for the scale of production, additive manufacturing is on the low side, up to 1,000, okay, as high as 2,000 units. But for injection molding, it could be upwards of 1 million units. For tooling investment, additive manufacturing have low tooling investment as the investment will be in the initial setup, while for injection molding, it will require a higher initial tooling investment. Going on to the cost per part, additive manufacturing would have very constant cost per part, while injection molding cost per part is directly linked to production volume, as shown in the previous case study. So for complexity of parts, additive manufacturing can build highly complex parts, but for injection molding, this will be directly linked to more complexity. For time to redesign, additive manufacturing has very low reiteration costs, while for injection molding, to redesign a mold from scratch requires a long lead time. So lastly, material costs. So AM obviously has its drawbacks in high material costs, and compared to injection molding, which uses resin, which has very low material costs. So moving on next, we'll be talking about additive manufacturing systems, specifically open systems and compared to proprietary AM systems. So the benefits of open material AM systems includes adaptation. Okay, so these open material systems adapts the materials that you are currently using. So you doesn't need to redesign the entire manufacturing line to slot in the machine. So you have a freedom of material choice. You will be able to use competitively priced third-party materials, which directly leads to cost saving. This will allow you to develop in-house new materials that you'll be able to use for your products. So you'll be able to produce functional prototype that can be used in a final part instead of using a substitute to create a visual prototype. This will reduce time to market for your parts. And lastly, design for additive manufacture. So consolidating many parts into one digitally and then printing the consolidated as one piece is something that cannot be done with conventional manufacturing. This makes AM cost effective by dramatically reducing manufacturing operations, inventory, labor, and certification costs. A reduction in material waste and weight can further increase the value of AM parts. So comparing between AM, open material systems, and proprietary AM systems. So adaptation, both systems can effectively adapt to your current manufacturing line, but with the freedom of material choice being a big factor. So with open material systems, you can use in-house developed materials while you can reduce the cost of proprietary material. So you are able to develop new material in-house, while proprietary AM systems will lock you out of using your own materials, and you have to use their materials to build your prototypes. So moving on to functional prototype, both systems are able to build, but that is when the material from the proprietary AM systems matches what you are going to use in the final product. If the material from the proprietary AM systems does not meet your requirement, you can only produce a visual prototype, leading to tick and a cross for proprietary AM system. And lastly, design for additive manufacture, both systems can do that. So topic 4 will be integrating of AM into current manufacturing. So the benefits of additive manufacturing can be broadly divided into two categories. The front end, where you can easily visualize, is shorter time to market, ability to re-prototype and redesign in hours, faster and cost efficient for low production runs, less material wastage, consolidation of assembly into single parts, and support AI-driven design methods. On the back end, you will be able to improve your supply chain efficiency, have on-demand production, lower your inventories, and you'll be able to produce and optimize legacy parts, which has lost the toolings and molds capable of producing the parts. So moving on to design freedom, okay, some of the challenges. So consumer prefers for intimacy and mass customization. This would lead to high operation costs and complex manufacturing chain. So the solution would be to automate production of complex parts, utilizing low-cost, high-strength 3D printing materials. Okay, so for a case study, so this complex assembly configured using jigs that are fully bespoke to one-off build. So the main challenge will be to maintain high mix, low volume production. This forces skilled labor to focus on solving the problem instead of coming up with creative engineering solutions. So the solution will be to use 3D printing to create jigs made from thermoplastic. This will allow the designers the freedom to create complex routing schemes and free up skilled machine labor. So this has resulted in 70% savings, cost reduction from $3,500 to $1,500, and 2x savings of overall production time. Next will be engineering grade durability. So the challenge will be to meet high industry standards, which will equate to frequent replacement, long tail time for specification. So the solution, quick implementation of solution would be to design and print components parts in-house. So as you can see this, the 3D printing part is this bracket here. So the imperfect specification causes bracket to wear, resulting in replacement every 2 weeks. So the long lead time of replacing the parts is about 4 to 6 weeks at about $250 per part. With 3D printing, the engineers are able to produce engineering grade components in-house at a fraction of the cost. And they are they have the capacity to make design adjustments with less design collaterals. So they are able to make the custom bracket within 24 hours at about $40 in material costs. So this has resulted in reduced reliance on expensive third-party services and able to maintain the level of quality while keeping costs low. So next will be the accurate and reliable repeatable parts. Challenges for reliable and agile prototyping for business success. So high accuracy and durability is needed. So the solution will be to 3D print to support prototyping with durability and accuracy. So one of the case studies is that maintaining agile manufacturing processes to win highly competitive contract from key customers in military and medical industry. So the company have to rapidly reiterate and deliver products in the form of proof of concept prototypes. Using traditional manufacturing, this will require 2 to 4 weeks lead time and over $5,000 per mold for each reiteration. With 3D printing, you will be able to print the mold in 24 to 48 hours for 97% less than the industry average cost, helping to deliver proof of concept products to win valuable contracts. So the result is a 97% cost reduction compared to current industry standards, and 1 to 2 days production time compared to 4 to 6 weeks of traditional manufacturing. Next, I'll introduce Maha suites of additive manufacturing capabilities. So this is Maha Chemicals Industry Solutions portfolio. We will be focusing more on the products as highlighted. So going back to the definition, we have a few machines that are in this lineup. So firstly, it will be material extrusion, represented by Poland AM and ZMOF. Next, we will be showing product videos on this. So firstly, we will watch the ZMOF introduction video.
There's no sound.
Sorry for the confusion. Just now is a product introduction on Poland AM. Next will be the product introduction on ZMorph. Next up in our lineup would be Shining 3D, representing carrying SLA. So next up in our lineup would be Fastwound Technology, carrying SLM and SLS. Okay, last but not least, we have technology that is not listed on these 7 categories. This would be Arburg, okay, represent using Arburg plastic forming technology. So we'll watch a short video to introduce on this technology. So our company is able to ascertain your technology readiness level. Okay, it's divided into 2 stages. Firstly, we are able to do a feasibility test and initial trial of your company to test on the processability of your parts. Then we will build simple parts and assess your business case, leading to a custom solutions for you. After building a custom solutions, we're able to do design freeze and validations. So we'll do process parameter optimization and build real application parts, leading to a core solutions for your company.